Okay. So, as a reminder, everything that I write in the OneNote here in class, you guys have, right? It's going to go into your shared OneNote. Everything that we say is recorded, video post, usually end of the day, but 8th hour, it's hard to get that uploaded before I go home. And once I get home, there's dinners and bath times and bedtimes, and it just sometimes doesn't get posted the same day. Sometimes it's the next day. But you have that. It's all going to be there eventually. Just as a reminder. You weren't here. Today, we're going to be starting Chapter 1. Chapter 1 is largely a review and maybe a slight extension in a couple of areas of things that we looked at in our algebra or algebra 2 classes, or maybe even some pre-algebra stuff. So again, I recognize that some of us had varying levels of good and bad experiences at these kinds of classes. I'm not going to, if I'm doing something that you're like, I have no clue what this is, you're acting like I should know and I don't, make sure you say something. We can always go back. Usually I'm trying to start pretty far back so that I can get everybody at a place they're relatively comfortable at. But if you find that's not the case, let me know and we can always scoot back a little bit more. Especially early on, the goal is not to lose anybody here in the first week or two, because it's going to make for a long year because there's nowhere else to go, right? Okay. So today, we're going to start by talking about functions. This is a word I hope we all recognize from either Algebra 1 or pre-algebra or Algebra 2. In fact, Algebra 2 is all talking about functions, right? That's like the entire course. It's just function this, function that. Does anybody remember a definition for like what a function is? Okay, that's all right. Oh, yes.
Every input has an output or something.
It's pretty darn close, yeah. So at the most fundamental level in mathematics, we're talking about sets. That's like our fundamental mathematical object. And a function is a rule or a set of instructions or a description or a pairing that matches up the things in one set, or I should say everything in one set, uniquely to something in another set, right? So put a little bit more technically, we say that a function from a set D to a set R is an assignment or a rule or a description or a pairing or whatever you want to use that verb, such that every element is just fancy for member of the set, right? Every element in D maps uniquely to an element in R. The set D of all the input values we refer to as the domain, and the set R of all the output values we call the range. Hopefully all those terms sound familiar. You talk a lot about domains and ranges in Algebra 2, right? That's a pretty standard Algebra 2 topic that you would have spent a little bit of time talking about. So let's take a few minutes and kind of talk about functions and ways to represent functions, and like with using those different representations, how we can decide whether something's a function or not, and just do some practice and kind of talk through what we're looking for, right? So starting way back to kind of where you would have started in the first chapter of Algebra 2, right? This sounds, and even you probably did some of this stuff in Algebra 1, although, 3 years ago, who can remember that much? Hopefully you do. All right. So let's say we have one set here. This will be our set D, our domain. So the oval is going to represent that set D. And then the dots inside of that oval are going to represent the members of that set. I'm going to just label those members x1, x2, and x3. The oval I've labeled R is going to represent my range set. The dots inside of that range set represent the members of that range, and I've labeled those members y1, y2, y3. And then in blue, maybe I'll pick a different color that's looks a little bit more different than black for those of you in the back. We'll use this light blue color. That's pretty. So these arrows that I've labeled F is my function. It's the set of instructions that describe how I'm pairing up the things from the domain with the things in the range. Everybody's okay with that? The question is this pairing that I've drawn, does that represent a function? The answer should be yes, right? So the two things we have to check is that every x goes somewhere, right? We see that, easy to see. And we need to check that for each of those x's, they only go in one location. So only one arrow leaving each x. Those are the two things we need to check for it to be a function. We see both of those, right? So every x has to go somewhere, and each of those x can only go to one location. Everybody feel good? This ringing bells, feel familiar? Good. Okay, let's look at a couple other examples. Just FYI, this thing that I've drawn here has a name. This representation of a function is called a mapping diagram. Good. You've got a good memory because you probably only talked about these for like a day or two in Algebra 2. If you did remember that, or if you're being sarcastic, I appreciate the sarcasm. Okay. So let's do it again. Now let's use our pretty light blue. So let's say, so that's going to be our mapping. Does this represent a function? No, you said no. Why not? Yeah. We have a member of our domain that doesn't go anywhere, right? The fact that x3 is unpaired means that this is not representing a function. Feel good still? Okay. All right. Do a couple more of these. I find this representation of a function a good start or starting representation because it's so visual, you know? It makes something that's really abstract feel a lot more concrete. Does this pairing represent a function?
Yes. No.
I heard some yeses and some nos. Those of you that said no, why do you think not? Okay, so x1 and x2 are going to the same range, but are they just going to one place? Yes. Are all the x's going someplace? Yes. Is it a function? Yes. So the fact that some domains are going to the same range, that is okay. The fact that we have a range that isn't used, that is okay. The fact that we have some ranges that are used more than once, that is okay. A function is only concerned about the things in the domain, the x's. All the x's have to be used, they are, and they can only go to one place. Each of them just goes to one place. This is a function, regardless of what's happening in the range. Does that feel okay? Good. Again, not uncommon for people to say yes and no on these. It's a review, right? Some of us got it and remember it. Some of us, the refresher helps. I appreciate the participation, like giving it a shot, taking a risk, making a guess if it's a guess or whatever. Like, that is all okay. Is this one a function? No, Jake, you shaking your head no. Why do you say not?
There's one range, x3, that's running two different applications.
And when you say range, you meant domain, right? Okay. So, yes, the problem here is x3 going to two different ranges. That's great. Feel okay? Another way we can represent a function is with a set of ordered pairs. So when we say ordered pairs, what do we mean? Like a point, an x, y, right? Like x comma y in parentheses, right? So if I'm talking about a set, my list is going to start with a curly bracket to indicate that we're talking about a set. And then if this is of ordered pairs, the things in my set should be ordered pairs. Yuck. So here's a set of ordered pairs. Again, what is this really representing? Well, I have a collection of x's. In this case, my domain would be 1, 2, 3, 4. Going to a set of y's. In this case, my range would be 1, 2, 3. Remember that in sets, there are no repeated members. So even though 1 was used twice in the range, when we write our range, we just write it once. Everybody's okay with that? Yes. Oh, you can walk to the bathroom even. It's not that big of a rush. I'm just playing with you. Sure, you can take the pass. You don't have to if you don't want to, though. I know sometimes it's a lot to carry. Right? You know, if you're trying to go to the bathroom, it's like one, I can't hold on to all this stuff at the same time. It's a hassle. I get it. All right. So when we're given a set of ordered pairs, there's two things we need to check, right? That all the domains are used. Well, that has to be the case if I'm given a set of ordered pairs, because if it wasn't, it would mean I'd have like an ordered pair that starts like 5, comma, and then nothing with it. Would we ever write an ordered pair that looked like that? No. So that part of the definition is always going to be satisfied if you're looking at a set of ordered pairs. The thing we have to check is to make sure that the domains are only going to one place, which really just boils down to I just need to check to see if any of the x coordinates are used more than once. So if I look, all the x's are different. Everybody agree? So all we can, that's it. That's all we needed. We have a function. As long as the x's are different, function. Does that look familiar? Remember talking about this last year, maybe? Start of the year. I know it was a long time ago. It's like, Mr. Kulik, that was like 365 days. I know. It's tough. Life is tough. Oops, that's not what I wanted to do. Bless you. You're welcome. All right, let's look at this set of ordered pairs. Does this represent a function? Andrew, you're saying no. Why do you say that?
Because the domain is repeated.
Yes. Great job. I loved how the way you phrased the answer, very specific. The domain x equals 1 is used twice in the point 1, 1 and in the point 1, 2. I think he's serious. All right. Now, these two representations we've looked at so far, the mapping diagram and the set of ordered pairs, when you talked about functions in Algebra 2, did you use those representations a lot? It was probably in just that first couple of weeks of school, and then you never saw them again, right? What are the more common? What's another representation for a function that's more common? What a graph, right? You looked at probably a lot of graphs in Algebra 2 to represent functions. So let's take a look at some graphs and talk about how we can tell if something's a function or not based on its graph. So let's say we have this guy, this graph. Does this graph represent a function? Okay, so Jacob, I see you shaking your head yes. Why do you say yes? That's a thing, yes. Yeah.
Every x value for the x line has its own y.
Great. So what Jacob's saying is that we can do something called a vertical line test. What we're looking for there is if there's any vertical line we can draw, should only intersect the graph in one location. So like no matter where we draw that vertical line, it's only going to hit the graph once. Call that a vertical line test. I always abbreviate that as VLT. You're welcome to do that also. So yes, this guy would represent a function. Usually we always remember, well, most students remember the vertical line test. Again, it has a name, that's nice. It has an abbreviation, that's nice. How about this graph? Does this graph represent a function? No, right? Almost any vertical line we draw is going to intersect this graph more than once. Everybody happy there? This is usually easy for us. Mr. Kulik, like, what's the trickiest thing you could do? This seems really straightforward. Well, I mean, the trickiest thing I could do is something like this, I guess. Does that represent a function? No, why not? Yeah, there's one place where I can draw a vertical line that intersects the graph in more than one location. It's the place where the point is overlapping the curve, right? So again, this would not be a function, but that's like the sneakiest I could do. And after you've seen it, it's like, that's not even all that sneaky, right? Okay. And now you probably saw a fair amount of, fair amount of time you represented your functions with graphs last year in Algebra 2, but that probably still wasn't the primary representation you used, right? The primary representation we use to describe a function is probably an equation. So let's look at that. How can we tell if an equation represents a function? So let's say we have something like x squared plus 2. Well, what do I do with this? It's not really clear, right? Well, what could we do? Maybe if we turn it into one of the other representations, it'll be more obvious what to do. What other representation could we turn this into easily? A graph. Great. How would we want to do that? And how are we going to get the picture to draw it? What tool would we use? Our graphing calculator. Yeah, let's do that. I mean, you could use a stylus to draw it, sure, but... So what I'm going to do, I'm just going to take out my graphing calculator and turn it on. To graph something, I'm going to press the y equals button. I'm going to clear out anything that I might have had written in there. And I'm just going to type in the equation as it looks on my sheet of paper. Notice that the y equals part is already on my calculator. So I'm just going to be typing the x squared plus 2. So the x button is next to the green alpha button. And then I'll press the squared command, which is like 3 down from the green alpha button. And I'll just type the plus 2. Now, it's probably been like 3 months since I've opened up my graphing calculator and turned it on and tried to do anything with it. Who knows what the last thing I was trying to graph was and what window I was looking at with it. So probably the first time, I'm going to press the zoom button and pick the Z standard option. That'll just reset my window back to the normal size. So if I was doing anything funky with it before, have a nice appropriate window. So there's my graph. Does this represent a function? Absolutely, right? It's just that U shape. Now, you certainly, with what you learned last year in your Algebra 2 class, could have done this without having to graph it. Ideally, again, not necessarily remembering this on the first day, you would have noticed that, hey, this is a polynomial with an x squared as our largest degree term, right? A polynomial that's degree 2 is a quadratic. Remember that term from last year? The graph of a quadratic is a parabola, either a u that opens up or a u that opens down. Hi, come on in. Thanks, Charlie, for you. I don't think so. So you guys kind of remember that? Do you remember how to tell from looking at the equation whether the parabola is going to open up like a U or down like a hill? So you look at the leading coefficient. So in this case, what's our leading coefficient? 1, right? Since that number is positive, your parabola would open up. If that number was negative, it would open down. Does that ring a bell? Yeah, maybe. You'll take my word for it right now. You're the math teacher anyways. I assume you're not telling me fibs. Wouldn't it be funny if I did a whole class where I just told you all the wrong answers on how to do things? You'd be like, no, would not. Or you're like, I feel like I've had that class before. Maybe you have. I don't know. I'm just joking. All right. What if we did it this way? What if I did that? Does that represent a function? Are you sure? Okay. So maybe it's not super clear. Some of us have an inkling, yes or no. But maybe it's not clear. What's the problem with what I've written here? Can I do the same trick that I just did? Why not? Great, because the y isn't by itself, right? Everybody agree? Now, what we could do is we could rearrange this to put the y by itself so that we could type it into our calculator and try. Just need to do a little bit of algebra to do that, but certainly within our means. Let's say we decided to try to do that. What would be our first step we'd want to do to try to get the y by itself? Yes, sir?
Subtract 2.
Great. Yeah, subtract 2 from both sides. Okay. Then what should we do? Great. To cancel the squared on the y, we use a square root. So we'll do a square root to both sides. Now, what do we have to be careful about when we square root both sides of an equation? What do we have to remember to do? What? Yes. Who said that? Good job. That's a tough thing to remember, right? Whenever you square root both sides of an equation, you do generate a plus or minus. We're going to put the plus or minus on the side that the square root will stay, because on the left or the right side of this equation, we know the squared is going to cancel the square root, right? That's why we did it to both sides. So this ends up y equals plus or minus the square root of x minus 2. Okay, y is by itself, but what problem do I still have typing this into my calculator? Do you have a plus minus button on your calculator? No, but the calculator can still handle this. All we're going to do is just type it on two separate lines. One line is going to be positive square root x minus 2, and the other line will be negative square root x minus 2. We're going to graph those two lines together, and that'll represent the graph for plus minus square root x minus 2. So notice above the x squared in blue is the square root symbol. To get to the blue commands on our calculator, we need to press the blue second button before we press that x squared. So I'll do one where positive square root x minus 2, and then I'll do one with a negative square root x minus 2. Make sure you use the negative symbol and not the subtraction symbol. You get a syntax error if you try to use subtraction there. And then I'll hit graph. What did we get? Not a function. Some of us had an inkling that that was going to be the case from the get-go. And certainly, based on what you would have done in your Algebra 2 class, and the fact that we had the picture of y equals x squared plus 2, you could have reasonably been able to tell what the graph of x equals y squared is going to look like. Does anybody have any intuition of how you could have used one to get to the other? So you remember that the term inverses from Algebra 2? One of the steps in finding an inverse is swapping the x and y in your equation, which is what we did, or what I did on these two examples, correct? They're identical except the letters x and y were swapped. So these two are inverses of each other. If you had an excellent memory and had a good Algebra 2 experience, you would have remembered that the graphs of two inverses are reflections across the line y equals x. So you could have been able to tell that that would have been your picture. And immediately that fails a vertical line test, right? Now, what I just did was that was a deep pull from Algebra 2. If you're like, I don't remember any of those things, it's okay. We're going to talk about inverses all over again later this chapter. My expectation is not that you would have that level of recall on the first day that we're talking about things. Okay? So don't panic on that. If what you just saw was like, you said a bunch of stuff that I don't remember, it's okay. We're going to do it again anyways. Was all right? Okay. But realistically, you could have done what we did just by graphing it, right? After I've shown you the graphing, nothing there was like crazy difficult or outside of reasonable expectation of something I could do, especially if I've seen it happen once or twice before. All right. So on these last two problems, or last two examples, we answered them. We said one is a function, the other is not a function, right? We made a little bit of an assumption in doing this. Does anybody know what the assumption is? I shouldn't even ask this because it's such a deep pull. I've asked this question like 2 other times and nobody's even come close to what I'm looking for here. Maybe we should just say it, right? So the assumption that we've made in both of these instances is that x is the independent variable and y is the dependent variable. Now, it's okay that we've done that because really through our entire mathematics career, that's what we've always used x and y as, right? X has always been the independent variable and y has always been the dependent variable. But what if, for example, instead of x's and y's, what if I had written it this way? And I used like r and s. Which one's the independent variable and which one's the dependent variable? Well, it's not clear at all, right? There's no, I don't have any baseline assumption that like, hey, x is always domain and y is always range. X is always the independent, the input. Y is always the dependent or output. I don't have any of that kind of, you know, a lifetime of algebra to fall back on to make an assumption with. Here it's not clear, right? That's the problem of kind of writing the equation with 2 variables, like an x and a y or an r and an s in this case, is that it's not always clear, depending on the letters we're using, which one is the independent variable, which one is the dependent variable. So we have another notation that we can use where that is clear. So let's look at that. That other notation is called function notation. So rather than writing y equals x squared plus 2, we would write f of x is equal to x squared plus 2, where this tells us that f of x is a function of x, i.e. that x is the independent variable and f of x is the dependent variable, as it clearly depends on x. That's all this function notation is doing, is it's designed to remove the ambiguity of r equals s squared plus 2, where you're like, which one is the independent variable, which one's the dependent variable? If I write it this way with a function notation, it's immediately clear that whatever is in the parentheses, that's your independent variable. And then f of that variable is the dependent variable, right? That's all it's designed to do, is just identify independent and dependent variable. Can I use y equals and f of x equals interchangeably? Do they really mean anything different? No. No. They mean the same thing. You treat them the same way. The only difference is the f of x gives you that extra layer of telling you explicitly the x is the independent variable. That's all it's doing. Is everybody okay with that? So if I had written instead f of s is equal to s squared plus 2, instead of r equals s squared plus 2, I would know immediately that s is the independent variable and f of s is the dependent variable, right? And then it's immediately clear what to do. Is that feeling okay? So that's the point of function notation, but it has an additional advantage. And that additional advantage is I can use some abbreviations for common tasks. So for example, let's say I have y equals x squared, or let's use something different, like 3x plus 4. And say we ask the question, what is y when x equals 2? Well, all that's telling me to do is plug 2 in for x and evaluate. 3 times 2 is 6, and then 6 plus 4 is 10, right? One of the other advantages of function notation is this whole statement I can make in 4 characters. Instead of needing an entire sentence to say this with function notation, I can do it with 4 characters. F of 2 tells me the same thing as asking the question, what is y when x is equal to 2? In function notation, I can just say f of 2. Or what is f of 2? So it's telling me to do the same thing. Now, inherently, mathematicians are lazy people. We don't want to take a sentence if we can invent a notation to do the same, say the same thing with 4 characters. So one of the things that makes mathematics more challenging the deeper you go in is because in addition to the mathematics part, there's almost like a foreign language aspect to it, where like we're introducing these new symbols and these new notations, and I have to remember what things mean and what that says and what to do when I see that set of symbols. And we're going to be talking about those sorts of things as we go. But if you're ever seeing something and you don't remember what that means or what that says or how to read it, ask. If you're unclear about the notation, it's important, right? If we don't know what the symbols mean, we certainly can't answer a question with the symbols in it, right? Do we all kind of remember function notation from the past, though? This is something I think we usually do a pretty good job of at any level of algebra. That's our first section. That was 1-1. Next up, we're going to talk about section 1-2, where we're going to talk about domains and ranges, which again is a set of terms that we should be familiar with from our Algebra 2 class. I think you do a lot with domains and ranges typically in your Algebra 2 class. That's certainly a first semester point of emphasis. So when describing a domain and range, what we're going to be describing is a set. So there's two different kinds of ways to describe sets, right? We can have a set that's finite, where it contains just like a fixed number of elements, like 7 things, or 8 things, or 26 things, or 10,436,852 things, but like a finite number of them. It is something you could write down on a list and eventually finish. And then we can also have infinite sets. Sets that contain an infinite amount of things. In those situations, you could never list every item because you would go on and on and on forever. So to describe these two different sets, we're going to use two different notations. In a finite set, it's acceptable to just do our squiggly brackets and just list the members of the set. So if I have a set of ordered pairs, and I want to describe the domain and range, I can just do the squiggly brackets, list the x's, and do the squiggly bracket and list the y's, making sure that no numbers repeat, right? If anything's repeating, we just write it once and be done with it. Everybody's okay with that? Usually that's not a problem. In an infinite set, we can't just list the things because there's infinitely many members. We would never get done. We could work on it our entire life and never finish, which is really sad way to spend a life, trying to write a list that you'll never be able to finish. Instead, what we're going to do is we're going to use a different descriptor. In this class, we're going to use something called interval notation. So an interval notation is just a way to describe an infinite set without having to use a list. So an interval notation is telling us, okay, I need everything bigger than something, or everything less than some number, or everything between two numbers. Right? That's all we're saying with an interval notation. It's just we're going to describe an infinite number of numbers by saying like, yeah, everything bigger than that, or everything smaller than that, or everything between these two things. Is everybody we okay with that idea? Now, you might be saying, Mr. Kulik, what do you mean, like everything between two? How's that infinite? Like, I want all the numbers between 0 and 1. There's an infinite number. There's infinitely many of those in between 0 and 1. Right? You have 0.1, you have 0.01, you have 0.001, 0.0001, and you see that we could do this forever, right? There's an infinite number, and between any two real numbers, there's infinitely many between them. Because you can always just tack on the decimal, right? Everybody's cool? Okay. So the way we set up an interval notation, the format for this is we write a number called the lower bound. The lower bound should be something that's smaller than every other number in our set. And it should be the largest such number that's smaller than every number in our set. So it's like the lowest number that's not actually, that's like borders on our set, right? And then we need an upper bound, which is the smallest number that's still bigger than everything in our set. And then we need to indicate whether those boundaries, the lower bound or upper bound, are actually members of the set too. And we do that by either using a parenthesis or a bracket. A parenthesis means that value is excluded from the set. And a bracket would mean that that value is included in the set. Did you guys use interval notation last year? Okay. Just like I like double checking. If you don't remember doing this, that's fine. We're going to do it. I'm doing it again from first principles, trying to do it in detail here. Anyways, so before we go and start describing domains and ranges, let me just take a couple of sets written as inequalities and work on translating those into interval notations. And then we'll go and look at some functions and talk about domains and ranges first, just to get used to doing interval notation again, because it's been an entire summer and we forget. And that's okay, as long as we remember later when you get some reminders. So let's say we have -5 is less than y is less than or equal to 10. If you guys remember from your algebra class, this is called an AND inequality. So my suggestion, especially if you're not very comfortable with doing writing an interval notation right away, is to start by translating this set of inequalities, or this inequality, onto the number line. So let's default back to like an Algebra 1 skill and try to connect it to something we're already familiar with. So if I look on my number line, I know this is going to involve -5 and 10. And if I look at this piece of it, -5 is less than y. Or if you read it from the right to left, you'd say y is greater than -5. Everybody's okay there? So when I start drawing this on the number line, the first thing I need to do is draw a point at -5. Should I be using a filled-in circle or an open circle at -5? Open, excellent. Why does it need to be open? Very good, because the inequality is a strict inequality. It's not an or equal to inequality. And then which way should my arrow be pointing? To the right, because we want the y's that are greater than -5. Things greater than -5 live to the right of -5. Maya? Absolutely. Then we'll look at the other half. Here we have y is less than or equal to 10. So on the same number line, I'm going to draw this inequality. So at 10, should my circle be closed or open? Closed. Why? It's the or equal to inequality, right? And which way should my arrow be pointing? To the left, because it's y is less than or equal to 10. The things less than or equal to 10 point to the left. And really what we have, since those two arrows are pointing together and it's an and inequality, is I just have this, right? Is everybody okay with that idea? All right. So let's translate this now into an interval notation. It's really easy because the lower bound is just going to be the number involved furthest to the left. Oh, okay. And the upper bound is just going to be the number involved that's furthest to the right. Open circle means that -5 is excluded. So that's going to be the parenthesis. Excluded means parenthesis, or open circle means parenthesis. And filled circle means included, so I get a bracket. Note here that parenthesis, open circle, and strict inequality are all kind of meaning the same thing. Similarly, bracket, open circle, or equal to inequality are all kind of meaning the same thing. Does that feel okay? Let's do one more and then we'll move forward. Let's look at this OR inequality. Usually nobody has trouble remembering that this is called an OR inequality as opposed to an AND, since it literally has the word OR in it. So here we have A is less than -2, or A is greater than or equal to 5. Just like before, let's start by writing this on the number line. So I'm just going to write each of these two inequalities separately on the number line. So A is less than -2. Since it's a strict less than, I'm going to use the open circle at -2. And because I'm looking for the A's that are less than -2, I need to point my arrow to the left because that's where the things that are less than -2 live, like -3, -4, -5. My other inequality is A greater than or equal to 5. Since it's an or equal to inequality, I know I'm going to have the filled in circle. And since it's A is greater than 5, I know the things that are greater than 5 live to the right of 5, like 6, 7, and 8. So I'm going to have my arrow pointing to the right. The AND inequality should always have the arrows pointed towards each other. The OR inequality should always have them pointed away. If you have them both going the same direction, you've made a mistake. Well, Mr. Kulik, they're not overlapping. What am I going to do with this? Well, it turns out what you're going to do is you're just going to use two separate intervals to do this. And we're going to connect those two separate intervals with this big letter U. U is just stands for the word union. That just means or in set talk. So since this was one inequality or another inequality, that's our cue that we're going to need to use a union there to connect the two. And we're going to need to use two separate inequalities. So far, so good? Okay. So let's look at this first arrow. Notice that really only one number seems to be involved, right? Let's start with the lowest bound. What's the smallest value involved in that inequality on the left? What's the smallest number involved? Negative infinity, right? Very good. Since that arrow is continuing to go to the left forever, there's no smallest number, right? The concept we give to, the name we give to that concept is negative infinity, right? That's like a symbol that represents this is getting as small as you want it to be. It's smaller than every other number, no matter how small you want to make it. Our upper bound then, the number furthest to the right, is obviously then the 2. Now, infinities whether it's a positive infinity or a negative infinity, whether you're using it as a lower bound or an upper bound, it does not matter. They always get a parenthesis. Because an infinity is not actually a number. X can't actually equal infinity. It's like a concept, right? So it's always going to get a parenthesis no matter where it's at in any interval. Everybody's got that? Okay. Should the -2 get a bracket or a parenthesis? Parenthesis, because the circle is open, because it was a strict inequality, which means that number is not included, because -2 is not less than -2, right? -2 doesn't satisfy our inequality. So it should not be included in our set. It should get a parenthesis. It should be excluded. But -2.000001 should. Everybody's okay with that? Okay. Let's look at the next spot. What's my lower bound on this inequality? 5. Very good. And the upper bound should be positive infinity, because I have the arrow going to the right. Excellent. The 5 should get a bracket or parenthesis. Bracket, because it's a filled-in circle or an or equal to inequality. And the plus infinity always gets a parenthesis. Parenthesis. Is this coming back? Yes.
For the negative infinity too, why did you just make it like that?
Oh, that's just a mistake. Thank you. Thank you, thank you, thank you. Yeah, it should be -2. I just got excited and missed it. If you see me making a mistake, don't hesitate to interrupt. If you think I've made a typo, don't wait till I'm all the way done to get me. Like, interrupt and tell me beforehand before we get through an entire problem. And this one, it wasn't bad because it's just one symbol to replace. But if it's like, you meant a -2 and I did like a whole bunch of calculations afterwards, it's like, oh my God, how this is erasing I have to do now. If you see me making a mistake, stop me immediately. Even if you're wrong and it's not a mistake, it's okay. It just tells me you're paying attention, you're following along, which is a great thing to be doing. Everybody's cool? Okay. How's the speed? Am I going too fast? Sometimes I get excited. Are we doing okay? If you need me to slow down, you can always ask, right? It does me no good to just bulldoze through all this and leave everybody behind going, oh, I just feel like I had math pounded at me for an hour and 20 minutes. I didn't catch any of it because it was just too fast for me to absorb anything. Okay? I get going sometimes. I just get excited about math. And then I start talking fast and writing fast and going fast, and everyone's like, oh my God, I can't keep up. If you catch me doing that, you're allowed to raise your hand and be like, Mr. Cook, can I have a minute to just kind of like catch up here and absorb some of this? That's totally fine. Okay? All right. So let's start talking about domains and ranges now that we've covered how to write an interval. So when we talk about domain, there's really two kinds of domain. There's something called an implied domain. Actually, I'm going to just copy and paste this in. And then a relevant domain. So let's, we'll look at the words here, but then I'll talk about like what this really means. So the implied domain of a function is the set of numbers that are algebraically possible from a given function. The relevant domain of a function is the set of numbers that logically fit based on the given situation. The relevant domain will always be smaller than or equal to in size the implied domain. So imagine you have a function that's just symbols and has no context to it. Like f of x equals 7x divided by 3. No context to this. We don't know what x means. We don't know what f of x means. It's just numbers and symbols, right? The only thing we care about there is an implied domain. Everybody's okay with that? If instead, you know, f of x represents the profit after selling X number of sandwiches, that now has a context attached to it, right? X is representing the number of sandwiches sold. So what kind of numbers can't X represent? Well, you can't have negatives, right? There's no such thing as a negative sandwich. And let's assume that there's no such thing as a decimal sandwich, like you can't have you can't sell 1/10 of a sandwich, right? You can really only have, you know, non-negative whole numbers, like 0, 1, 2, 3, 4 sandwiches, right? So that's going to be a relevant domain because there's a context, a meaning attached to the variables. So we have to think about, okay, in the real world, what kind of numbers make sense for this context? Right, if we're talking about numbers of sandwiches, as opposed to, say, like the length of something. Again, lengths probably aren't negative, but you certainly could have decimal lengths, right? There's nothing wrong with that. You can have half an inch, 1/10 of an inch, 1/millionth of an inch. As long as you have an instrument careful enough to cut it, you could certainly have that. So context is really what the relevant domain is about. You have to think about the situation a little bit. Everybody ready to do some examples? Okay. Who's getting tired? I am exhausted. All right, so let's do the domain and range. For this one, we'll start with the domain first. As an aside, you'd always have to do the domain first. You could never do range first. Okay. So in this problem, is there any context to what x and f of x are? No, just symbols and numbers, right? So I don't care one whit about a relevant domain. It's going to be the same as the implied domain. So all I have to do is think about that. So to think about my implied domain, what I think about are the operations involved in my function. If I look at 2x times the square root of x minus 4, I see 3 operations. I see multiplication. I have 2 times the square root of stuff. I have the square root operation. And I have the subtraction operation. Does everybody see the 3 operations going on here? So now I'm going to ask myself, if I multiply 2 numbers, do I always get a third number as a result? Can the multiplication of 2 numbers ever be undefined? Well, no, of course not. If I multiply 2 numbers, I always get a third number back, right? How about subtraction of 2 numbers? If I subtract 2 numbers, will I always get a third number back? Of course I will. Okay, well now let's look at the square root. If I take the square root of a number, do I always get another number back? No. What kinds of numbers get me in trouble if I start square rooting them? Negative numbers, exactly, right. So if I take the square root of a negative number, we get an imaginary result, right? And up until last year, we didn't even get imaginary results. We got undefined, right? If you type that into your calculator without the settings set up the right way, it says error, non-real answer, right? So that's the place where I have to worry about for an implied domain, is I know I can't take the square root of negative numbers. Imaginary things don't count as domain outputs, right? Because when we plot something, you don't plot x comma imaginary thing. You can't do that. Everybody's cool? So what I care about then is I know that whatever I'm taking the square root of has to be non-negative, right? It has to be greater than or equal to 0. Anything that's less than 0 is undefined. Everybody's okay with that? So I'm just going to take the stuff under the radical, and I know whatever the x's I can plug into, that part has to be non-negative. Now, what does this look like? It looks a lot like these examples we just did before, right? Where it's just an inequality that I'm going to translate to an interval notation. So first thing I'm going to do is add 4 to both sides so that the inequality just has a variable on one side of it. Now notice when I added 4 to both sides, I didn't change the direction of my inequality. It continued to be greater than or equal to. Do you remember when you have to change the direction of your inequality? Because you do that sometimes. Does anybody remember when we have to do that? It's if you multiply or divide by a negative, right? That should ring a bell after I said it. It's like I see some head shaking. Oh yeah, that's what it is. All right. So just like before, now I'm going to go ahead and draw this on a number line. Because it's an or equal to, I'm going to use the filled in circle. Because we're looking for the x's greater than or equal to 4. Those are the numbers to the right of 4. So when I write my interval notation, 4 is the lower bound. And because we continue going right forever, positive infinity is going to be my upper bound. Eden? I didn't. Sorry. Out front?
Yeah.
I don't care about it. Because multiplication is never going to create something undefined. So it doesn't matter to me. It'll matter with our range. But for the domain, the multiplication can't cause something to be undefined. So the only stuff I care about is the stuff that can cause the function to become undefined. In this case, it's the stuff underneath the radical is the only thing that can cause this to be undefined. The stuff under the radical has to be greater than or equal to 0. Or else, whatever is outside doesn't matter. The function is undefined. Does that feel okay? All right. So the 4 gets bracket or parenthesis? Bracket, excellent. And the positive infinity gets parenthesis. And now, if you looked at your answer key, there's going to be one other piece to this. In front of this, it's going to have an X, and then looks like a C with a bar in it. All that part is saying is that X is a member of the set blah. Why do we use X here? Because we're talking about domains. X is always for domain. Does Mr. Kulik care if you don't write that part? No, it's fine if you don't. I just wanted to talk about what it is so that if you see it in the answers, you're not confused about what does this, what, huh? Is it wrong? No, it's fine. If you just label, in a question where I ask you to give me the domain and range, if you just wrote domain next to your answer and range next to the answer, that's fine. Or you could write X is a member of the set. That would tell me it's a domain. What would you put in front of a range? Y is a member of the set. Because we know Y's go with ranges. Whatever. Again, you could just write domain and range, the word next to it, and it's fine. Mr. Kulik's fine with that. Just wanted to be clear. If you look at the lesson or if you look at the answers, you'll see those things in there. I didn't want anybody to get go, oh, I don't know what to do. No, you're doing fine. It doesn't matter that if that's there or not to me. Okay. So now that we have the domain, we could do the range. Now the range is always going to be trickier than the domain because the range is the dependent variable. It's always going to depend on the range, right? I'm sorry, the range is going to depend on the range. That makes no sense. The range is always going to depend on the domain, right? The y is the dependent variable. It's always going to depend on the x. So what I want to do to start, I'm sorry, go ahead. Of course, yeah. What I want to do to start is figure out whether my function is always increasing, always decreasing, or doing some of both. Okay with that? So let's go back and look at this. So if I multiply 2 times a number, is that always going to, as that number gets bigger, is 2 times the number also going to get bigger? Yes, right? Okay. So now let's look at this piece. As I take the square root of a number, as that number gets bigger, is the square root of that number also going to be getting bigger? Yes, right? Do a little test case. Just pick some numbers that are easy to take the square root of. So square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. As those inputs got bigger, the outputs 0, 1, 2, 3 also are getting bigger, right? So this function that we're looking at is increasing all the time. Everybody agree? That as x gets bigger, y is going to get bigger also. Everybody's good with that? So what that tells me is that the lower bound for the range is going to come from the lower bound of the domain. So the lower bound for the domain was 4. So that gives me 0. Is everybody okay with that idea? Similarly, the upper bound for the range is going to come from the upper bound from the domain, which in our case was positive infinity. Oh boy, Mr. Gulick, that looks weird. And yeah, we don't really plug positive infinities in here, but we're just going to do it as kind of like a thought exercise. We're not actually doing this. We're just kind of doing it to kind of reason to ourselves what's going on. So let's think about this. Infinity minus 4. What's that have to still be? Still infinity, right? You can add or subtract anything from infinity if it's infinitely big. Taking something finite from it does nothing. Square root of infinity is still infinity, right? You take something infinite and you do anything to it, it's pretty much going to stay infinite, right? 2 times infinity then, still infinity. So this thing still stays as positive infinity. So my interval is going to be 0, comma, positive infinity. I know the positive infinity gets a parenthesis, but what should 0 get? Well, let's think about where did 0 come from? I got it from plugging 4 into my function, and 4 was the lower bound for the domain, which has a bracket on it. So that bracket from the domain is going to carry through to the range because I used that domain value to get the range value, right? So if the point 4 comma something has to be included, the something that goes with it was 0, so 0 also has to be included. Everybody's okay with that idea? Let's stop here. This feels like a good place to stop. We'll pick up the last little bit of this next time. At this point, you guys should be able to do like 1 through 12 from the problem set. Remember, when are the problems due? Sunday at midnight. They're due in the OneNote. We'll talk next time about if you're not writing your homework into OneNote, how to get it in there if you're doing it on a separate sheet of paper. We'll kind of go through an example of how to do that so that you guys can feel comfortable doing that if that's the route you choose to do. And you can do either one, right? You can do stuff on paper and upload a picture in. You can do stuff in OneNote specifically, just write it in OneNote. You can go back and forth, right? You can do some of each. It's not a big deal. Okay? All right. Good job today, guys.